Subrahmanyan Chandrasekhar, known to everyone as Chandra, was born on October 19, 1910 in Lahore, British India, now Pakistan, into a family of intellectuals and achievers. His father, Chandrasekhar Subramanya Iyer, was a civil servant in the British Indian government. His mother, Sitalakshmi Balakrishnan, was a woman of strong intellect who translated Henrik Ibsen's A Doll's House into Tamil. But most significantly, his uncle was C.V. Raman, who would win the Nobel Prize in Physics in 1930 for his work on light scattering, the Raman effect. Growing up in a family where scientific achievement was celebrated and expected, young Chandra was marked for greatness from the beginning. Chandra was a prodigy. He read voraciously, mastered mathematics early, and showed an intuitive grasp of physics that astonished his teachers. His family moved frequently due to his father's postings, but wherever they went, Chandra excelled. He was educated at home initially, then attended Presidency College in Madras, now Chennai, one of India's premier institutions. At Presidency, he encountered professors who recognized his exceptional abilities and gave him access to advanced texts and research papers. While still an undergraduate, Chandra was reading the latest papers on quantum mechanics and relativity, subjects that were revolutionizing physics in the 1920s. India in the 1920s was a complex place, still under British colonial rule, with a growing independence movement, caught between traditional culture and modern Western science. For a young Indian intellectual like Chandra, the path forward was clear. Go to Europe, study with the masters, make contributions to science, and perhaps return to help build India's scientific capabilities. In 1930, at age 19, having completed his undergraduate degree with highest honors, Chandra won a scholarship to study at Cambridge University in England. He would go to the center of the physics world to study with the giants, Eddington, Dirac, Rutherford, and make his mark. The journey from India to England in 1930 took 3 weeks by ship. And during those 3 weeks, on the deck of that ship steaming across the Indian Ocean and through the Suez Canal, 19-year-old Chandrasekhar did something extraordinary. He performed a calculation that would change our understanding of stellar evolution, reveal the fate of stars, and ultimately explain the existence of black holes. Using the newly developed quantum mechanics and Einstein's theory of special relativity, Chandra calculated what happens when a massive star runs out of fuel and begins to collapse under its own gravity. What he found shocked him. Stars above a certain mass couldn't stop collapsing. They would compress to infinite density, crushing matter beyond recognition. It was an absurd conclusion, almost unbelievable, yet the mathematics was clear. When Chandra arrived in Cambridge in 1930, he was entering the most prestigious physics department in the world. Cambridge had Rutherford, who had split the atom. It had Dirac, who had just predicted antimatter. It had Eddington, the great astrophysicist who had confirmed Einstein's general relativity by observing the bending of starlight during a solar eclipse. And it had the Cavendish Laboratory, where some of the most important discoveries in physics were being made. For a young Indian student, it was intimidating but also exhilarating. This was where he belonged, where his abilities could fully develop. Chandra began working on stellar structure, trying to understand what holds stars up against gravitational collapse, what determines their size and temperature, what happens when they run out of fuel. At the time, it was known that white dwarf stars, incredibly dense stellar remnants, with the mass of the Sun compressed into something the size of Earth, were supported by electron degeneracy pressure. This is a quantum mechanical effect. Electrons, being fermions, obey Pauli's exclusion principle and resist being squeezed into the same quantum state. This pressure can support a dead star against gravity even without any ongoing nuclear fusion. But Chandra realized there was a problem. When you compress matter to extreme densities, electrons start moving at speeds approaching the speed of light. At those speeds, you need to use relativistic mechanics, not ordinary quantum mechanics. Chandra worked out the full relativistic calculation, and what he found was startling. Electron degeneracy pressure has a limit. If a white dwarf exceeds a certain mass, roughly 1.4 times the mass of the Sun, the electron degeneracy pressure isn't strong enough to hold it up. The star must collapse further. But collapse to what? There was no known mechanism to stop the collapse. The star would keep compressing, potentially to infinite density, what we now call a black hole, though that term didn't exist in 1930. This was the Chandrasekhar limit. 1. For solar masses, the maximum mass a white dwarf can have. Stars below this limit end their lives as stable white dwarfs, slowly cooling over billions of years. Stars above it must undergo some other fate. Either they shed mass somehow, or they collapse catastrophically. Chandra's calculation was rigorous, based on well-established physics, quantum mechanics, and special relativity. He was confident in his result. In 1931, he presented his findings at a meeting of the Royal Astronomical Society. He was just 20 years old, a graduate student presenting work that challenged existing ideas about stellar evolution. And he was about to collide with one of the most powerful figures in British astronomy. Arthur Eddington was a titan of astrophysics. He had written the standard textbook on stellar structure, had made fundamental contributions to understanding how stars generate energy, and was one of the few people who fully understood Einstein's general relativity. He was knighted, internationally famous, and held in awe by the astronomical community. He was also Chandra's supervisor at Cambridge, though in practice, Chandra worked independently, as was common for advanced students. Eddington had initially been supportive of Chandra's work, but as Chandra developed his ideas about the mass limit and stellar collapse, Eddington grew increasingly uncomfortable. Eddington didn't like Chandra's conclusion. A star collapsing to infinite density? Matter being crushed beyond recognition? It seemed absurd, almost obscene, a reductio ad absurdum of relativity, as Eddington put it. He believed there must be some mechanism, some physical process not yet understood, that would prevent such catastrophic collapse. Stars couldn't just disappear into singularities. Nature must have some way of stopping the process. Eddington's objections weren't just scientific, they were almost philosophical, aesthetic. The universe shouldn't work that way. In January 1935, Chandra was scheduled to present his work on stellar collapse at a meeting of the Royal Astronomical Society in London. He had refined his calculations, extended his analysis, and was ready to present a comprehensive picture of what happens to massive stars. But Eddington, also scheduled to speak at the same meeting, had other plans. After Chandra finished his presentation, Eddington stood up and delivered a devastating critique. He argued that Chandra's results were wrong, that they violated physical principles, that they led to absurd conclusions. He dismissed the idea of a mass limit for white dwarfs and suggested that Chandra had made errors in applying relativistic quantum mechanics. For Chandra, this was a nightmare. Here was the most respected astrophysicist in Britain, his own supervisor, publicly demolishing his work in front of the entire astronomical community. Chandra tried to defend himself, but Eddington was implacable. The audience, faced with a choice between the famous Eddington and the unknown Indian student, sided with Eddington. Chandra's work was dismissed. Papers he submitted were rejected or ignored. His attempts to get his ideas published in major journals were blocked. Eddington's opposition wasn't just scientific disagreement, it was a campaign to suppress Chandra's results, to prevent them from being taken seriously. The psychological toll on Chandra was immense. He was in his mid-20s, far from home, facing not just scientific criticism, but what felt like a personal attack from the man who should have been his mentor. He became depressed, isolated, uncertain about his future in astrophysics. He completed his PhD in 1933, but the controversy over his mass limit overshadowed his achievement. He felt stuck, unable to move forward with his research, unable to get recognition for what he knew was correct work. It was one of the most bitter scientific controversies of the 20th century. A young genius with the right answer, crushed by an establishment figure who couldn't accept the implications of that answer. In 1936, facing a hostile environment in Britain and realizing that Eddington's opposition would prevent him from getting a proper academic position there, Chandra made a difficult decision. He would leave England and go to America. He accepted a position at the University of Chicago's Yerkes Observatory in Wisconsin. It was a good position at a respected institution, but it was also a kind of exile. Cambridge was the center of the astrophysics world. Wisconsin was the periphery. Chandra was leaving behind the colleagues, the resources, the prestige of Cambridge, but he was also escaping Eddington's shadow and finding a place where his work might be appreciated. America proved to be good for Chandra, though the early years were difficult. He threw himself into teaching and research, working on a variety of problems in stellar structure and stellar dynamics. He was a demanding teacher, brilliant, thorough, but also intimidating and exacting. Students remembered his lectures as masterpieces of clarity and rigor, but also as exhausting, requiring intense concentration and preparation. Chandra expected excellence from his students because he demanded it from himself. He was extraordinarily productive, publishing paper after paper, slowly building a reputation in American astronomy. But the controversy with Eddington continued to haunt him. Eddington kept publishing papers arguing against the mass limit, kept insisting that Chandra's conclusions were wrong. And because Eddington was so respected, many astronomers remained skeptical of Chandra's work. It wasn't until the late 1930s and 1940s when other physicists, particularly Hans Bethe and J. Robert Oppenheimer, confirmed Chandra's calculations and extended his work, that the Chandrasekhar limit began to be accepted. Oppenheimer and his student George Volkoff showed that even neutron stars, supported by neutron degeneracy pressure, had a mass limit around 2-3 solar masses. Above that, nothing could stop gravitational collapse. The conclusion was inescapable. Massive stars must collapse to form what would later be called black holes. Vindication came slowly, painfully. By the late 1940s, most astrophysicists accepted that Chandra had been right all along. Eddington, who died in 1944, never admitted he was wrong, but his objections were increasingly seen as based on aesthetic prejudices rather than physics. The Chandrasekhar limit became a cornerstone of stellar astrophysics, fundamental to understanding stellar evolution, supernova explosions, neutron stars, and black holes. But the damage to Chandra's career had been done. He had lost crucial years to the controversy, had been forced into exile from Cambridge, had suffered psychological wounds that never fully healed. In 1953, Chandra married Lalitha Doraiswamy, whom he had known since childhood in India. She had studied in England and America and became a key support in his life, managing his household so he could focus entirely on his research. They had no children, and Chandra's life revolved around his work. He was reserved, formal, intensely private, not given to casual friendships or small talk. Colleagues respected his brilliance but often found him distant, difficult to know. He lived for physics, for understanding the universe through mathematics and physical law. Everything else was secondary. Having established the Chandrasekhar limit and seen it finally accepted, many scientists would have rested on their laurels, continuing to work on variations of the same theme. Not Chandra. Over the following decades, he embarked on a remarkable intellectual journey, systematically working through different areas of astrophysics, writing definitive monographs on each, then moving on to entirely new fields. It was an unusual approach. Most scientists specialize, going deeper and deeper into narrower areas. Chandra went broad, mastering one field after another, each time producing work of lasting importance. In the 1940s and 1950, he worked on radiative transfer, how radiation moves through stellar atmospheres. His book, Radiative Transfer, became the standard reference. In the 1960s, he turned to stellar dynamics, the behavior of large groups of stars in clusters and galaxies. His Principles of Stellar Dynamics transformed the field. In the 1970s, he worked on the mathematical theory of black holes, using general relativity to understand their properties. His Mathematical Theory of Black Holes, 1983, was another masterpiece, dense, rigorous, mathematically sophisticated, covering everything then known about black hole physics. What drove this relentless productivity? Partly it was work ethic. Chandra worked long hours, every day with almost no vacations. But more fundamentally, it was his aesthetic sense. Chandra believed that physics should be beautiful, that the equations describing nature should have elegance and structure. He was drawn to problems where mathematical beauty intersected with physical importance. He would master a field, find the elegant mathematical framework underlying it, write the definitive treatise, and then, crucially, move on to something new. He didn't want to spend decades working on minor variations of problems he'd already solved. He wanted to conquer new territories, to experience again the thrill of mastering a new domain. This approach made Chandra somewhat unusual in the scientific community. He didn't build a large research group with dozens of students working on variations of his ideas. He didn't create a school of Chandrasekhar disciples. He worked largely alone or with a few close collaborators, pursuing beauty and understanding for their own sake. He won numerous awards: the Gold Medal of the Royal Astronomical Society, the National Medal of Science, election to the Royal Society. But he remained somewhat apart from the astronomy community, respected but not quite one of the crowd. Chandra was also a devoted servant of science in other ways. He served as editor of the Astrophysical Journal for 19 years, from 1952 to 1971, transforming it into the leading journal in the field. He reviewed every submitted paper personally, made editorial decisions with rigor and fairness, and maintained the highest standards. It was unglamorous work, enormously time-consuming, but Chandra saw it as his duty to the community. He also continued teaching throughout his career, giving courses at the University of Chicago even when he was in his 70s, maintaining the same demanding standards he'd always held. In 1983, at age 73, Subrahmanyan Chandrasekhar was awarded the Nobel Prize in Physics for his theoretical studies of the physical processes of importance to the structure and evolution of the stars. It had taken nearly 50 years from his discovery of the mass limit to the Nobel Prize, one of the longest gaps between discovery and recognition in Nobel history. The prize was shared with William Fowler, who had worked on nuclear processes in stars. Chandra gave his Nobel lecture on the mathematical theory of black holes, bringing his career full circle, from calculating stellar collapse as a 19-year-old on a ship to understanding black holes as the inevitable fate of massive stars. The Nobel Prize brought Chandra international recognition, but by then he was already revered within the astrophysics community. The Chandrasekhar limit had become fundamental to understanding stellar evolution. When astronomers observe supernova explosions, they're seeing stars that exceeded the Chandrasekhar limit. When they study neutron stars and pulsars, they're studying objects formed when stars collapse beyond what electron degeneracy can support. When they observe black holes, now confirmed to exist at the centers of galaxies and in binary systems throughout the universe, they're seeing the ultimate result of the gravitational collapse that Chandra first calculated. The applications of Chandra's work extend far beyond what he originally imagined. Type Ia supernova, explosions of white dwarfs that exceed the Chandrasekhar limit, are now used as standard candles to measure cosmic distances. These measurements led to the discovery of dark energy and the accelerating expansion of the universe, one of the most important cosmological discoveries of the late 20th century. Chandra couldn't have known in 1930 that his mass limit would eventually help reveal the fate of the universe itself, but that's the power of fundamental work. Its implications ripple outward in unexpected ways. In his later years, Chandra turned to a subject that had fascinated him throughout his life: the relationship between science and art, between mathematical beauty and aesthetic truth. He gave lectures on the beauty of scientific theories, comparing the elegance of general relativity to great works of art and literature. He believed that the pursuit of beauty was a legitimate guide in science, that theories possessing certain aesthetic qualities were more likely to be true. This wasn't mysticism. It was the conviction, born from decades of experience, that nature's laws have a mathematical elegance that we can perceive and appreciate. Chandra died on August 21, 1995, in Chicago at age 84, having worked almost until the end. He left behind a monumental scientific legacy: the Chandrasekhar limit, foundational books on radiative transfer, stellar dynamics, and black holes, and a model of scientific excellence characterized by rigor, breadth, and aesthetic sensitivity. In 1999, NASA launched the Chandra X-ray Observatory, one of the great space telescopes, named in his honor. The Chandra Observatory studies high-energy phenomena in the universe, supernova remnants, neutron stars, black holes, the very objects whose existence Chandra's early work had predicted. Looking back on his life, Chandra's story is one of both triumph and injustice. His early confrontation with Eddington was a travesty, a young scientist with the right answer, crushed by an establishment figure who couldn't accept it. The cost to Chandra was enormous. Years of his career, his position at Cambridge, perhaps even his emotional well-being. But Chandra's response to this injustice was remarkable. He didn't give up, didn't become bitter or stop working. He moved to America, found a position where he could work freely, and spent the next 60 years producing research of exceptional quality and breadth. The Chandrasekhar limit stands as his monument, a fundamental constant of nature, as important to astrophysics as the speed of light or Planck's constant. Every star in the universe is subject to it. When a star exhausts its nuclear fuel and begins to collapse, this limit determines its fate. Stable white dwarf below the limit, catastrophic collapse above it. It's the dividing line between quiet stellar death and violent transformation, between white dwarfs and neutron stars, between stability and singularity. That a 19-year-old student calculated this on a ship in 1930, using physics that had been developed just a few years earlier, is remarkable. That he had to fight for a decade to get it accepted is tragic, but that it now bears his name and will be remembered as long as astronomy exists is the final vindication. Subrahmanyan Chandrasekhar showed us the fate of stars, revealed the existence of cosmic singularities before they were called black holes, and demonstrated through his own life that beautiful mathematics and rigorous physics can unlock nature's deepest secrets. His journey from Lahore to Cambridge to Chicago, from rejected student to Nobel Laureate, from the ship calculation to the Chandra X-ray Observatory, is one of the great stories in the history of science. The stars remember. Every white dwarf hovering just below 1.4 solar masses, every supernova explosion from a star exceeding that limit, every black hole formed from stellar collapse, all testify to the insight of a young man who dared to follow the mathematics wherever it led, even when it led to conclusions that seemed impossible, even when the greatest astrophysicist of his time told him he was wrong. Chandra was right. The universe is stranger, more violent, more beautiful than Eddington could accept, and we understand it better because Chandrasekhar had the courage to calculate the impossible.